Should we move to the next talk? So Annette will be talking now about sample preparation. The talk is for 45 minutes again, and then we'll have some questions and the break. Thank you, Annette.
Okay, good. Next one, I will share my talk again. This one I kept a little bit shorter. Let's hope that I don't talk too much so that there's a bit more time answering questions. Okay,
Thank
so
you.
sample preparation deserves always its own talk because it is really, really important when it comes to the quality of our data. And what I will do in this talk is more tell you a little bit about the different options and why it is important, because rather than giving you just a range of recipes, but I will give you later also some further literature and tips and tricks where to look for specific recipes. But of course, depending, it's a versatile technique. There are many different materials that you might want to analyze. And so it can really depend on a case-by-case basis what is exactly needed and what kind of equipment you have access to. So when it comes to sample preparation for electron microscopy and microanalysis, there are certain general rules that they all have to comply with. And specifically even down to electron microscopy, which means that you only want to just look at samples, maybe get first order compositional information, but not necessarily like the highest precision data. Already samples have to be able to withstand a vacuum. They have to be stable under the electron beam, and they either need to be conductive or we have to apply a conductive coating because we bombard them with electrons, and so charging can affect. The lowest effort sample preparation that in this case you can do is just taking your material and applying it on an SEM stub and coating it. So here are some examples which would allow you to image the sample and maybe get a rough idea what elements are in there. However, if you want to do analysis both on a scanning electron microscope with EDS and on an electron microprobe, you need a flat and polished surface. In addition, usually we have to cut down the samples because the actual space that we have for the size of samples is usually much more restricted in an electron microprobe compared to a scanning electron microscope. And so commonly we find thin sections, specifically in earth science departments, because there's additional light microscopy work, petrographic analysis that people want to do. But other types, epoxy pucks and all that can be possible too. Important is, again, different vendors, different models of microprobes have different types of holders. And so the specific dimensions and number that we can fit into a single holder at a time can differ quite a bit from lab to lab. So if you are planning to do analysis or you're thinking about it, a good step is always to contact whoever is in charge of the lab and ask what are the dimensions that you can accommodate. There are also subtle differences between European thin sections and North American thin sections in terms of their width and thickness. And so you don't want to find out on the day you do analysis that you're a little bit off to what can be available. Okay. So as I mentioned, they all need to be flat and polished, but otherwise there are a couple of different form factors that you can find thin sections. 1-inch epoxy mounds where you just embed the materials are also very popular because you don't have to hit the target thickness like with a thin section. And there are sometimes also other holders where a surface can just be polished, and you can use some kind of vise to bring it in. The downside of that is often that it makes it more likely that the sample is tilted. And usually a good microprobe sample holder is top referenced to minimize any sample tilt. What does a good polish mean? The final polish that should be better than 1 micron as the final step. And this is what we usually refer to as mirror-like finish. And so if you're unsure if your polish is good enough, there are 2 steps. First is like, if it's not shiny, you're not good enough. That's like, it should, the surface should like equally reflect back. And if that is achieved, you can check your polish under reflected light microscope or even under stereo microscope, where I just angle the surface so that, again, it reflects back. And that is oftentimes already a good indication. Like, if it's not good enough in this view, for sure you will run into problems during analysis. And then, of course, if you can, just looking at it in an SEM or something might be helpful, but usually just like reflected light microscope is a good enough step to do that. If they are not polished well enough or not polished well enough throughout, there can be all kinds of problems. So why do we care? Why do we need that? And even if you do EDS on an SEM, it's like, there are certain things that apply to everything. So it's you're not getting good, just because the EDS tends to normalize to 100, doesn't mean that you're getting accurate and good data. So the first thing is that surface roughness can cause shadowing effects or imaging artifacts. So if you just look at something specifically in secondary electron images, but also backscatter, you can have artifacts that have nothing to do with a difference in composition that's just coming from it. And even more, these artifacts tend to be directional depending like where your spectrometer is looking at it. And so only when you're better than 1 micron, because of the wavelengths of the X-rays and everything else, you're not having these kind of problems. Then I talk in my third talk more about the specifics of matrix corrections, but again, absorption is a big part of it. The depth at which our X-rays are being generated have an important effect, and we usually compare the intensities that we're getting on standards. And so if the standards are well polished, which they should be, any kind of difference in surface roughness can lead to higher or lower intensities. So for example, if you have the X-rays are being emitted all throughout and need to go again to a certain spectrometer or detector, and so if they have to travel through a topographic high relatively, there's a longer absorption path, so our intensities might drop because they have to travel through more materials, versus if there are a lot of depressions from scratches or something, there might be less absorption before the X-rays are being emitted, and so all this affects your intensities, and so it changes the differences in what intensities you're getting, and more importantly, to what degree this effect takes place depends then on the X-ray line. So you can't just normalize it to 100. You will overcorrect certain elements and you will undercorrect other elements if you just normalize it. I also mentioned, so to give you a little bit more ideas how that looks like is, this is a really nice paper on Monte Carlo simulations where they looked at rough surfaces. So their case here that I show is a surface roughness of 2 microns, so almost the final polish that we want. And what you see here is the intensity ratio relative to polished surface. So at 1, you would get exactly the same intensities as a polished surface, and then you can lose down to 8% or have higher values up to 5, depending on the topography. And so 3 is supposed to be the relative midpoint, where it's the same as the surface polished, and this would be a topographic high, and this would be a topographic low. And here are example for a nickel K alpha, aluminum K alpha, and a nickel L alpha line. And as you can see across that, so in a material that contains nickel and aluminum, it depends on what X-ray line you analyze, but also what element, you can lose up to 8% of your intensities just by having a final polish of 2 microns. Then sample tilt can also be a problem. So this is a similar type of graph, where here at 0 we have no tilt, and then we have a positive tilt and a negative tilt relative to our standard, and here is the X-ray intensity ratio. So this would be an untilted sample, and here we see a couple of very light elements, and these are usually very low energy X-rays that get easily absorbed versus titanium K alpha. And so you see, like, titanium K alpha needs a significant tilt to show a reaction, but an element like boron, carbon, and eventually there comes silicon, it can be like 50% increase, 80% drop. That's kind of the range that we see here. So very pronounced effects specifically for light element analysis. So proper sample preparation is really, really critical for the success of your EPMA work. And you can put so much effort into the analysis itself. If your samples are not in a good shape, it will affect your data, and it will specifically affect your data that is difficult to trace, because again, you can analyze them standards and they will come out great. But like each spot will then be a reflection on your sample of like how much surface roughness is there. And different minerals polish usually slightly differently, and different crystallographic orientations can polish differently. And so you get like this very random erratic data set, and wonder what's going on. And none of, again, normalizing doesn't work. There are no magic things that can correct your data set when it comes to that. Usually I do think leave it to the professionals. If in doubt, there's a real learning curve. There are less and less places that have a dedicated sample prep person on staff, which is a shame. And to me, very short-sighted. There are usually a lot of companies where you can send things, and they have a lot of experience with doing analysis. But I've also seen labs where they're like, oh, let just the students do it. And that's like, the results are not always great. And you spend hundreds of dollars for analysis to save $50 on sample prep. That often is not the greatest choice. Then also important is when you have your samples and they're great, keep care of them. Like going to and from the sample and all that to the lab, you can ruin good samples, of course. So what are the options? Again, I will give more information just as a literature collection. But if you do it yourself, specifically mounting medias are very commonly done in-house. There are different types where you just embed your material, your sample, in a mold with some resin and have it cure, and then you polish the entire thing. There are different types of molds, silicone molds, plastic molds available for that. And you can make grain mounts on a adhesive surface and then fill it with it, or you have like larger samples. And important is that usually if you have a porous material, they should be vacuum impregnated before cutting and before embedding. And my personal tip, like specifically if you do grain mounts, people use all kinds of adhesive, including just like normal packing tape. But if you have very, very small grains, and so you just want to start out with like minimal polish. I'm a big fan of Captain Tape, that's the brand name. And that usually provides a very smooth surface for small grains. So I then usually just have to start polishing at 9 microns because I don't have to take much roughness away, and that helps me preserve these small grains. There are different types of resins that you can use. Just a few words to them. Usually we prefer epoxies, but it depends a little bit in what kind of field you are. So when it comes to epoxies, they have like good edge retention. That is important. We don't want to have gaps between the epoxy and the material, because then the samples can pluck out simply. They might not be held, but also it adds to charging problems, possibly. Usually they ideally want to have low viscosity for these epoxies, so that we don't create bubbles or pockets where the epoxy doesn't reach the sample. And usually epoxies take more time than other materials, but they tend to be harder and have good adhesion, which makes them preferable. Sometimes people also are using acrylics and also UV cured materials. And the advantage is that they are have a faster cure, but they can have a lower hardness, less adhesion, worse edge retention, which again depends then on the material that you're trying to embed. If it's something fairly big, like worse edge retention, doesn't necessarily is a problem in terms of like losing the sample, plucking it out. But it still can be a problem for charging. But if you have small grains, it might be a real problem. And also a problem with any kind of gaps and bubbles and otherwise can be that the polishing abrasive can be trapped in cracks, and then you like have contamination issues where you might scratch up in the next polishing step from that. And usually acrylics outgas a little bit more, and I give some examples a little bit later. And then what you see often also in old times, but also material sciences, they're like phenolic resins, like bakelite, that has a good hardness and stability, but usually can be problematic too, because samples can crack, or you can create gaps that can then cause contamination or be a problem. But one useful thing with phenolics is also that you can add a filler that can make themselves conductive. So if you have an already conductive material, you want to have either coated because the epoxy will not be conductive, or you want to have it embedded in a mounting media that is also conductive. So specifically with resins, they are not created equal, specifically when it comes to the emission of gas. And usually I find that the more quick curing it is, like if it's advertised with like, oh, it's set in 30 minutes, it usually means that it also has a strong emission of gases later, and can be a real problem then with pump down time in a scanning electron microscope or an electron microprobe. And the University of Edinburgh has a great little webpage on their SIMS site. I have the link in a moment, where they looked at various epoxy resins for certain like key factors. And so what you see here is the pump down time in minutes and the vacuum chamber vacuum. And again, it's a logarithmic scale, and you can see that the initial pump down can differ very much, and specifically what achievable vacuum we have. And the better the vacuum, the better our analysis, essentially. And so usually I'm a fan of slow curing resins and letting them sufficiently cure and not just like rush my whole prep, because that really helps then with a pump down before we can do analysis and overall quality of the data. So there's some general recommendations. Again, use a slow curing epoxy. It can really help to leave it in a vacuum oven for hours or overnight to cure and outgas. You don't want to have like, you know, you mix so much epoxy and then you're like, oh, it would be a shame. And you create these like overfilled mounds that have like a huge amount of epoxy. Having a bit more can be helpful when you polish to get it into a polisher or hold it securely, but it can be really helpful to then, when you're done with the polishing, to cut it off or grind it down. Again, you can have a certain thickness, but you don't want to have like an inch or something of just epoxy. And this webpage is just fantastic with like a lot of common resins. Here's some example, and they looked at viscosity and the goodness of vacuum that you get and the cure time and hardness and the gap and whatnot. And it can be very good to guide you what epoxy to get. Another good resource for you to look at is the vendor web pages. Usually they offer multiple different types. This is an example for strewers. Everything that I show is not like in terms of vendors and what types is not really it's just for your information. It's not that I endorse a specific product. Because again, it depends also what you're trying to embed. But there's a lot of good information that tells you like if it's good in terms of viscosity or good adhesion and so on. And that can be also helpful in deciding what epoxy to use. Then when it comes to mechanical polishing, we have to do it in multiple steps. There are choices when it comes to what lubricants to use and what kind of abrasives. So a few words for that. So usually we start out with our just cut off surface of the sample, and then we move on in multiple steps to finer and finer grits. Lubricants are usually used to help extend the life of the abrasives, but also minimize scratch depth and deformation. It also, if the sample is very sensitive to even minimal heat, can reduce friction and dissipate heat. So using some lubricants can be very helpful. And then there are different types of abrasive, either already like as a liquid with some lubricant, or you can have diamond films or grinding discs, and they can be sometimes really good to keep a very flat surface without preferential polishing of harder and softer materials. So when it comes to that, we can have polishing cloth, grinding disc, diamond lapping films. And again, it really depends on the material, what is better in a given thing. Sometimes it's also just what you have on hand. But specifically, if you have to buy supplies, it's worthwhile to see a little bit what might be the right kind for your range of applications in your lab. I really like diamond films often, but I don't produce samples for users in a large quantity. So it's usually more for my standard collection. And again, there are different types of diamond lapping films that can be used. And usually the recommendation that I heard is like, instead of doing each and every step, I divide by 3. So I might go from like 30 to 9 to 3 to 1. And then if I'm feeling that way, I go below 1. Then an important thing that I've seen in data can be a problem if you put too much pressure on your sample, you can really produce a certain amount of damage in the material. And so what this shows is kind of the depth of this damage. So oftentimes going from one polishing step to the next one, you still want to remove a good amount of material to get to the undamaged part again. And this is what this is supposed to show. Common problems of mechanical polishing are that, again, you get uneven surfaces. We don't want that. If we have a multi-phase material where the hardness really differs, then sometimes it can be also a real problem that abrasive can be embedded in soft materials, usually alteration phases. I can't tell you how many times we were like, oh, diamonds during an analysis, and then it turns out that all the diamonds are exactly 9 micron in size, and obviously even in a thin section, just like contamination from polishing. You can reduce that by thoroughly clean your materials after each step, specifically with an ultrasonic bath. Yeah, it's just something to keep in mind. And then usually soft materials require more lubricants and less abrasives, whereas hard materials require less lubricants and more abrasives. And if you, for each cleaning step and at the end, do not usually use like compressed air that you can get like just through a normal line. There are special handles or like endpoints for that can have a filter that can make it useful. But yeah, usually the compressed air can, if it's just the building line, can introduce water into oil. And so it's not a final clean surface anymore. Different ways then when you're done, usually you want to clean with some alcohol. When you're finished, there's also something called bioorganic soap that's specifically for abrasives, like if you do EBSD polishing with Cyton, that's good to replace it, and then letting the samples dry either for a specific time or speeding it up by having them in a vacuum oven or on a hot plate can also be useful, because again, it helps with the pump down time of when you put the samples in. Then not all samples are conductive, and so a lot of the earth science materials are natural insulators. So to avoid charging, we need to apply a conductive coating. Depending on the coating, there can be other pros for that, by helping with the imaging and reducing heat. There are all kinds of sputter coaters, evaporation coaters, and so on that can be used for that. And there are different types of materials. Usually we like for quantitative analysis carbon coating the most. It has a lot of advantages. It's chemically inert, doesn't react with the specimen, which sometimes can be otherwise a problem with metallic coatings. It's mechanically stable, so it usually lasts quite a long time, even if you transport it around. It's stable in the electron beam. It's you don't have a lot of contrast, and most importantly, unless you want to analyze carbon itself, there are no interferences with other elements compared to a gold metal coating or something. It's also cheap. The downside can sometimes be if you have porous samples or three-dimensional ones, it's that it's a unidirectional coating, meaning that the sides are not necessarily well covered. So that can be an advantage of metal coating, where you use sputtering for it. So if I have to analyze paper or something, I usually find that sputtering is better. We usually don't like sputtered carbon though. So just as a comment for that. Advantages of metal coating, again, if I want to analyze carbon, I usually have to find something else for the coating. Depending on the thermal conductiveness of the coating. It can help with beam sensitivity. People recommend silver for biological samples. As I mentioned, it is usually sputter coating is multi-directional. So if I have topography is good. But the main problem with metal coatings can be that they can oxidize themselves. So that is something to keep in mind, depending what metal you're looking at. But then there are like a whole range of materials, and there's like a really nice paper in Microscopy Today that goes into the pros and cons of the different types. An important part of the coating process is that the vacuum level affects the quality, and that's true for all kinds of materials. And specifically with a metal coating, there are like minimum coating thicknesses that you need to follow in order to actually get a conductive coating. Because in the first step of metal coating, you just have condensation, then you have nucleation, grain growth, and only in the coalescence step, you actually get a continuous film. And so different materials have different minimum coating thicknesses, and that can then be another thing to follow, where if you want to have a thin coating, you can't use certain materials, or other materials are more ideal for that. People are getting more interested in iridium coating instead of carbon. For quantitative analysis, your standards should be coated with the same material. So that depends then a little bit on the lab if that's an option. But it's specifically good if you want to analyze carbon coating. It's good for high resolution imaging, and iridium coating can be applied very, very thin to get good enough conductivity for analysis. And if it's a specific thickness, it has a similar absorption to carbon-coated samples, so then it makes it easier to compare it against carbon-coated samples or standards. After we've done with coating, we usually then apply, in addition, some conductive tape. It helps making the contact between the sample surface and the sample holder, specifically if it's not a top-mounted sample holder. There are different options, copper tape and carbon tape. Both work well. There are some people who have very strong feelings about which one. For me, it's usually if I have the samples for a long time mounted, carbon tape gets a little bit gummy and difficult to remove. The problem with copper tape, I would say, is that you really need to make sure that it has good contact. Like you really need to press it down for it to work well. So I think sometimes there's a bit more of a chance that the user doesn't do a great job. And then in addition, there are also conductive paints and conductive cements that you can get that help with conductivity. And then, so finally, very important, again, when you're done with all that, you really want to make sure that you keep it clean. This is like a graph from a publication on specimen contamination. I love it. Frowny face. So usually the problem is the human between the step where you get your specimen and putting it in a expensive microscope. So store your samples in adequate ways. Don't wrap them in random toilet paper. And that will all help with getting good analysis. And also then with the samples itself, like modern machines have very clean vacuum. And what I see now is that oftentimes any kind of contamination really, which can also then be a problem during imaging, really comes from the samples and the sample holders. So oftentimes before I coat samples, I don't only wipe the surface, I also wipe with alcohol the backside of a thin section, because I don't know who did maybe petrographic analysis while eating a sausage. So I really want to make sure that everything that goes into the machine is relatively clean. And the same is true with like where if you're in charge of the lab where you store your holders, keeping them in a desiccator and all that, ideally under vacuum. really helps with pump down and keeping it clean rather than having them lying around on a table somewhere or in a drawer. Again, there's a lot of useful literature, so I don't go into details. I don't give you recipes because it depends so much on what you have available and what is what your particular technique material is. But here are some good literature, and specifically if you have to embed to make grain mounts, embed very small grains, looking into the tephra literature. They also deal with small grains. There are some papers that have excellent step-by-step guidances and examples. There's also a good amount just on the internet. And specifically, when you look at tech notes from vendors, they want you to succeed. They want you to buy something and be happy with it. And so oftentimes, specifically when it comes to like how long with what kind of grid size, with what kind of lubricant, kind of recipes, is something that you find on vendor websites. And so it is worthwhile to look there, like videos and webinars as well, and so on, that are really informative when it comes to that. And then lastly, again, I mentioned they're like full-on recipes there on their material. So depending on here's a 4-step procedure for bulk mounts. Here's one for aluminum alloys, and it gives you all the information, including for polishes, automatic polishes, that can be worthwhile. Some vendors also sell demo kits for specific sample prep. So instead of buying like 10 or 50 polishing substrates, discs for each step, they have something where you get like one of each and you can see if that works for you. So that can be really cool. Or if you only have to prepare a few samples, that might be all that you need. And then I can't stress enough, again, if you have questions, don't come to me. I can't tell you how your titanium alloy needs to be polished. But who knows that are the application scientists at these companies. They will tell you how it works with their materials, but you have to buy it from somewhere anyway. And you can often translate it anyway. If they say this much grit for that long, doesn't matter what vendor it is. So these people are looking who is there. They're very open to that. They are researchers themselves, and they usually have to handle a large amount of questions from all kinds of things. So they're really good in knowing all kinds of tips or tricks for different materials. Okay, and that's essentially what I want to say. And otherwise,
Thank you, Annette.
To answer any questions.
Perfect.
Thank you, Annette.
We have the time for this.
Yes.
So there are 3 questions of the Q&A. Starting with Stuart, who says, what effect does the epoxy resin have on analysis? Sometimes I'm detecting chlorine in my analysis, which I presume is from the resin.
Yes. And that can be a real problem, specifically if you have grain mounts where you have constant contact of small grains with the resin. And so not all resins have chlorine, but some can have really high amounts. The Edinburgh website actually has a list of like compositions that's also that you can ask for it. Sometimes they can even though change between different batches, like when they reformulate their resin. So if that's something that is a concern, I would always make a test mount just like without anything in it, and just quickly see with EDS if you get a lot of sulfur. So common elements that you find in there are sulfur and chlorine, but some can also have sodium and silicon, so it can be really messy. And I definitely had it when I was analyzing apatites, that they all had positive zoning and chlorine towards their edges, and that was just the resin. John, do you want to add something to it?
Mm-hmm. Yeah, I had an interesting experience a while back where we were detecting chlorine at trace levels of like several hundred ppm first in some samples and then in all the standards. And we finally tried, it took a while, but we finally tracked it down to our carbon coater. And what had happened was one of the technicians had replaced the backing pump line with a non-food grade PVC hose. And that PVC hose was outgassing enough chlorine that it was backstreaming into the through the diffusion pump into the carbon coater chamber. And so once we replaced that hose, then it went back to normal. But it was amazing to me how it could be that much outgassing upstream from the diffusion pump. So just word to the wise, you always use food grade materials or better when you're, because and that said, everything is contamination.
Yeah. But yeah, so it's not always the epoxy. It can also come from things like that. I also seen it when people are not using spectrographic graphite for the coating. So sometimes it can be on the coating contamination, but yeah, definitely when it comes to epoxy resins, again, if you have to buy new ones, it's worthwhile to check through online or asking or checking the Edinburgh website if it's known to have high amounts of a certain element that may be something that you want to interest. And if you already have the epoxy and you're worried about it, just analyze, again, not with a focus beam. Like we don't want to, usually we try to avoid analyzing epoxy, but if you do it gentle with like a widened beam, it doesn't like vomits into your sample chamber and you still get some analysis, and that gives you information. Same as if you're interested in CL, they're like resins that are have more CL than zircons or apatites, and that can be a real problem when you take some when you're interested in that aspect. And likewise, there are other ones that are very low. And so sometimes before you mount all your stuff in the wrong type of resin, just making an empty epoxy mount and having a look is useful. Okay, another question?
Thank you, Annette. Can we move to the other question?
Yeah.
In case of loose powder, what would be the procedure to prepare polished surface?
Okay, yeah, powders are tricky and it depends a little bit on the grain size. So if it's a coarse powder, you can just like make a slurry with epoxy and then let that harden. And again, low viscosity epoxy, and that can be helpful. Of course, again, our analytical volume is usually in like a 2 to 3 micron range. So if your powder is finer than that, you have a problem with the analysis anyway, irrespective of how you mount it. And then, so in that case, I would refer you to literature on powder analysis. There is a good amount also there. And they, for quantitative analysis, use a peak to background method that is used. There are publications by Nicholas Ritchie and so on. But yeah, if it's a loose powder, otherwise you still need some embedding medium so that you can polish it.
Great, Annette. So next question is whether WDS is recommended on non-flat samples. And there are some comments underneath that, but let's see first if you can answer that, Annette.
Okay, so I already showed you a little bit in the talk that the graph, that it really depends on the X-ray line that you're analyzing. And so it again depends on the material. But again, it doesn't depend on the type of detector, because I often see people very sloppy with EDS analysis, which EDS is great if you are careful with all the usual steps. If you analyze something like iron, KL, like if you analyze a lot of the K alpha lines, you need a good amount of tilt to it significantly affect your data. But if you try to analyze light element, then a little tilt can be already a problem. So specifically, if you don't have a top referenced holder and can embed it, anything that you can do to minimize the amount of tilt of the surfaces that you're analyzing is important. If you're, let's say you want to analyze something that like a crystal that naturally has different crystal facets, go for the one that is the flattest and the least inclined. So it all is sometimes, and accept that the data might not be at its optimum. It's like we can get away with certain things, and sometimes we just do with what we have to do, but don't pretend that this is the same quality of data necessarily as a perfectly polished, perfectly flat surface. But again, the degree to which it's not the best really depends on the X-ray lines that you're looking at. And one can model that with Monte Carlo even, if you want to get a handle beforehand to see how good or bad it is in this case.
Perfect. Thank
And
you,
John?
Annette. There's
Yeah.
one last question, if you can briefly answer it, please. Will polishing with lower abrasive size, less than 1 micron, be beneficial or increases the counts for trace element and light element analysis?
For light elements, absolutely. Again, the problem with light element analysis is that they are all low energy X-ray line. Low energy X-ray lines are also L and M lines of other elements. So it doesn't always have to be strictly oxygen or nitrogen. It can also be that you have to analyze like the gold M line, which gives you the best peak to background. And those are very then susceptible to topography because the amount of absorption changes. And so the better the polish for these kind of materials, the better is your data. And that is both for accuracy dominantly, but can also be for the precision, like what specifically, like how tightly do you have to determine your concentrations to answer whatever question you have. So yes, at times it is a must, and other times it's a nice to have, like it never hurts. But it depends on the application, like how strict it has to be.
Perfect. Thank you, Annette. So I think now we're gonna go into the break and be back here at 4:15 for the next talk of Annette.
I'll just mention during the break here that I don't know if you've had a chance to try it out, Annette, but there's a new feature that I added a few months ago in the software where if you have at least 3 points in a sample and they're not in a line, then it will actually use the Z positions of those points to calculate a sample tilt, and then it will apply an effective takeoff angle to all your analyses. And I tested it out by putting a sample into the instrument. It tilted as much as I could, and it worked. So
yeah,
that was,
no, and absolutely. And that will be so useful for that, exactly. And yeah, so certain software, like the probe software, can now correct for sample tilt. And so again, it's not always possible to avoid it, but we're getting better and better in like dealing with the data and potentially correcting it. But that doesn't mean that we now can just ignore that and let the software do it. But it will make a significant contribution to even facilitating or correcting data after the fact where a thin section wasn't correctly slid into the holder.
Yeah, I mean, especially because, like, for example, when I analyze standards, I typically will measure n number of points just with an X offset. And since the X offset is in a line, you wouldn't be able to do a tilt correction on the standard. So it's certainly something to keep in mind, but it's not a cure-all, and it certainly doesn't deal with any rough surface roughness issues. That is something that you just have to fix in the polishing sample prep steps. And I have a question for you. Do you find that for the final polish, do you find that colloidal silica or colloidal alumina is better?
Colloidal silica is chemical abrasive, and so one of the big risks with colloidal silica is that you polish it too long, specifically as vibro polishers are so awesome, where you can just like, the polishing takes a long time anyway, 6 hours or something. And sometimes you might be tempted to say, let's make it 8. And the problem then can be that with if you have different materials, different minerals in it, that you create all this sample roughness. And mechanical alumina is mechanical abrasion. And so that tends to keep the sample more flat. And what I always wanted to explore, and now I don't have a vibro polisher anymore, so whoever wants to do it or has done it, I would love to hear about it. I always wanted to do like a combination of both, where I might mostly do colloidal aluminum and then just a little bit of colloidal silica to get a nice flat surface. But this is really important for EBSD analysis, dominantly where you need this deformation-free surface.
Well, so I was under the impression, I'm probably wrong because I'm not a sample prep expert at all, but I was under the impression that the colloidal silica was both a mechanical and a chemical polishing material, but maybe not. Maybe that's, I don't know. I do know that I've used both, and they both seem to work well for removing the carbon coat from old samples that need to be repolished and then recoated. But I don't know more than that. Someone's asking on the Q&A, they're asking, do you know the name of this tilt correction function in the Joule software? And I should mention that this correction is not in the Joule software or the Kamika software. It's only in the Probe software. So if there is a tilt correction in the Joule software, I don't know of it.
No, there is not.
There is not.
Okay. All right. And this is just a feature that I added in there because I was trying to, and if you go to our forum, you can read about it, but there's a topic called effective takeoff angles. And the idea is that I was starting to do some simultaneous K-ratio measurements where you basically take two materials that have a large absorption difference, and you measure the tune-up for that element, and then you measure the K-ratios on all your spectrometers that you can. And it doesn't matter if it's a different crystal or whatever, but as long as you can tune up to the same emission line. And what you would like to see, what you would expect to see, is that you get within statistics the same K-ratio on all your spectrometers. Of course, you actually find that you don't. And this is an acceptance test that Paul Carpenter suggested 30 years ago that we should utilize when we're testing a new instrument and making sure it's up to specs. And interestingly enough, I mean, from my perspective, the one thing that an electron microprobe produces, the one thing that it actually does is produce a K-ratio. Everything else is, physics software and normalizations and corrections and things like that. But the thing that in other words, you might think of a microprobe as a K-ratio producer, and that's really what it does. But this is the one test that is the most important test, and it's the one test that Kamika and Joule do not perform on their instruments. And I'm not sure why they don't do it, because it is the only thing that we care about the instrument. Does it produce consistent and accurate K-ratios? And what we started to find is that certain spectrometers, due to the alignment of the crystal or the alignment of the spectrometer, or maybe the instrument being improperly, there's a famous story of the microprobe at Caltech, California Institute of Technology, that took 6 years to get accepted because it turned out that JUL had accidentally mismachined the column, so the column was not in the center of the microprobe. It was off by a centimeter or something like that. And so I don't know but it was enough of a distance that it could be detected by the K-ratio, simultaneous K-ratio measurement. And it turned out to be multiple problems. One was crystals that were Bragg crystals that were diffracting asymmetrically, but also just misalignment of the column. And they actually had to get an entire new housing of the microprobe, the main chamber. They had to get a new one from JUL Japan in order to correct this. So this test can still be applied today. And so we want to see the same K-ratio on all our spectrometers, but in addition to that, we'd also like to see the same K ratios on other instruments if we're using the same two materials at the same accelerating voltage. So these are all part of this consensus K ratio effort by Nicholas Ritchie and I and others to make sure that the data that we're acquiring on our instruments is actually comparable. So first start with your own instrument, make sure that all your detectors, including your EDS detector, by the way, assuming it's the same takeoff angle, does give you the same K ratios. And then see if other, because as I will show tomorrow in my talk, we do not get the same answers from different labs, unfortunately. And it's a complicated problem, but we'll talk about that tomorrow.